Hi, this is AP Calculus section 5.3, inverse functions and the derivative of an inverse function. And so we're going to see a theorem that's going to be a little quirky. You got to get your head around it. Take your time with it, but you should be able to do that. So what I want you to do is warm up with these first three problems and find the inverse. You should be able to do that yourself. Go ahead and pause and do that, and then I'll show you the answers and we'll talk about them. Now for number one, we find the inverse of just a set of points. So all we do is switch the x and y coordinates around. That one should have been pretty straightforward, but that confuses some people who are not familiar with it. Now the second one, what you do is you switch x and y and solve for y. Now when we do this, we get f inverse is equal to x squared minus 7 all over 2. This only holds true for x greater than or equal to 7/2. I think I did that right. Let me check. And as it turns out, I'm absolutely wrong writing that statement right there. If we look at a graph, here's our original. And then here is the inverse. What happens is that x has to be greater than 0. So where did I get this statement? Well, this statement right here is simply the domain of my original up here. And so I'm just looking at that, but in this case, I need x greater than or equal to 0 because I'm looking at the inverse and not my original that I have. And only 1/2 of this parabola shows up just because I originally started with just one piece because it's a square root. Okay, let's look at this next one. If we do x equals, switch x and y, solve for y, there's a little trick you have to do here. You have to cross multiply to get to here and then distribute and then get all your y's on one side. So I'm going to move the y over here, and whatever's left, which is the negative 4x squared, I'm going to bring it over here. Now when I solve this out, I get kind of a plus or minus because I solve for y squared, take the square root of y squared, I get plus or minus. The problem is though, well, I don't know if it's a problem or not, but this thing is symmetrical about the x-axis. And in that case, the plus or minus doesn't mean anything. So if I look at the graph for that one, here's what I end up with. Here, the red here is my original. The blue here is my inverse. And notice the symmetry now. This purple line is y equal to x. And with y equal to x, I'm just switching the x and y coordinates, and so I have symmetry about that line when I take the inverse. And so if I have a point on this curve, be it maybe 7, 1, that means that the point on this curve over here will be 1, 7, even though we can't see that. Okay? So yes, we do have symmetry, and then that shows also that we do have an inverse function. So that these two are inverse functions, and we write this notation. This does not mean 1 over. This is just convenience notation, just wording that means f inverse. Okay, so if I'm talking about two functions, f and g, if they are inverse functions, f of g of x is equal to x and g of f of x is equal to x. You should know that from your pre-calculus days. Then f of x only has an inverse function if it is monotonic. Monotonic means strictly increasing. And this is if it's a, I'm getting a lot of flash in there, or decreasing, but not both at the same time. This is if it's a continuous function. If you have data points, then it might be a totally different situation. Okay? Now, if we move on here, f of x has an inverse if it passes the horizontal line test. What that means then really is that we are either increasing or decreasing. So if I look at this, if you remember what the horizontal line test does, if I take and do a curve like this, if I take the inverse of this thing, I'm going to end up with something like this. So now if this is f and this is f inverse, well, this is not an inverse function, so I can't even write that because the inverse doesn't satisfy the vertical line test. What you can do is to tell if something if the inverse does have a function, you can go ahead and look at the inverse directly, or you could have looked at the original, and instead of a vertical line test, you could have looked at a horizontal line test. So first of all, here f is a function, But if I do a horizontal line test and I intersect in more than one point, that tells me that the inverse is not a function. But really, you can just look at it and see if it's strictly increasing or strictly decreasing. If I'm strictly increasing like this, if I take the inverse of that, that's no problem because I switch x and y. Something like this is also called one-to-one. What that means is that for every x, there's one y, and for every y, there's one x. And so it's kind of double duty on our function talks that we talked about in Algebra 1, etc. Okay, so it has to pass the horizontal line test. Graphs are said to be one-to-one. I just mentioned that. And then if they are inverses, they're reflected over y equal to x. That's because if I have a point AB on 1, so if f has the point AB, then G, if G is its inverse, the point BA is going to be on that curve. With that, we just have the symmetry over y equal to x. Okay, now if we want to show that we have two inverses, we must show, I'm having trouble right here. Okay, I think I fixed it. But we must show f of g of x equals x and g of f of x are both equal to x in order for these two to be inverses. So I go f of g of x equals, I'm going to take this function and put it inside this function. So wherever I see the x, I'm going to put big parentheses. And inside, I'm going to put the g function, which would be x minus 2, the square root of that. So if I simplify this, the square root goes away, so it's x minus 2 plus 2, which is simply equal to x. So I satisfied that one. Then if I do g of f of x, I need to show that that's equal to x as well. So I take the g function, that's my outside function. Wherever I see the x, I'm going to put big parentheses. Then inside, I'm going to put in my f of x, which is right here. So x squared plus 2. So x squared plus 2 minus 2, those will go away. So this is equal to the square root of x squared, which is equal to possibly plus or minus square root of x, but plus or minus x. But I'm going to use x just because we already established that x is greater than 0 for this. Okay? So both cases work out. So g and f are inverses. I went through that quickly, but that's kind of how you prove that f and g are inverses of each other. And then if we want to find the equation of the tangent line of f and find the equation of the tangent line to g at x equal to 6 and f of x equal to 2, let's look at this and see what happens now. So I have these two functions, and they tell me that f of 2, if I look at what f of 2 is, well, f of 2 is equal to 6. Well, what's g of 6 going to equal then? Well, g of 6, if I plug it in there, square root of 4, that would be 2. And so what happens with both of these? Well, let's graph them and see. This point 1, 2, 3, 4, 5, 6. Here's my point 6, 2. 2, 6 would be right here. And if I graph the tangent line, can you tell anything about these two tangent lines through these 2 points? Well, how about if I go like this and dash out y equal to x? Anything? Well, hopefully that you see that if my two curves are inverses of each other, what happens to the tangent lines at their respective points? When I say respective points, well, 2, 6 on one of them and 6, 2 on the other one. Those would be corresponding points, would probably be a better term. Well, what happens is that the slope of these things are just going to be reciprocals of each other. Here, I'm going to rise up a certain amount and run a certain amount. Well, that's equivalent to my run over here and my rise. And so the x's and y's just change with each other. Okay? So then my slopes are going to be reciprocals. So at any particular point that are corresponding points, the slopes are reciprocals. Right? So what's going to start happening is that I'm going to look at f prime and compare it to g prime, and those two would be reciprocals. Okay? That's kind of the theorem that will be coming down the line a little bit. Now let's look at these, and do these have inverses? This one, strictly increasing, looks like it. You might say, well, it flattens off there. Well, I still think that the point just before that is less than, and the point just after that is greater than for the y values. And so I think I still am strictly increasing. So this would be a big yes. We do have an inverse for this one. What about number 2? Yes or no? Well, if I pull out my old horizontal line test, first of all, the one that I'm looking at is a function. But I'm talking about the inverse. The inverse would not be a function because this horizontal line on the function is a vertical line on the reciprocal. I'm sorry, not the reciprocal, the inverse function. And so the inverse is not a function, so it does not have an inverse. And the sine function, I think you can tell that right away. Oh, so good. So that's a no. This one does not satisfy the horizontal line test, and so the inverse is not a function. We'll have to try to look at what happens to the inverse sine later on. You've seen that possibly, but we might have to limit the domain so that it is strictly increasing or strictly decreasing. Oh, that's what I just answered right here. So yes, at certain times you can limit these things. So if I went right here, yeah, this piece would be strictly decreasing. So I could find the inverse of this piece. And we deal with piecewise functions all the time. So this would be yes, you can. Okay? Going on to the second page. Some of the theorems that we'll discuss. Reflective property of inverse functions. We already kind of talked about this. AB is on one, and BA is on the other one. Here's the picture. And from your geometry days, if you reflected, that means that you're at a perpendicular. If you connected the 2 points, you're at a perpendicular to the axis of symmetry. And with that axis of symmetry, then you're going to be equidistant from that center line, or that axis of symmetry. Okay, so that's a nice little picture for you to look at when we're talking about two functions that are inverses of each other. Now, continuity and differentiability of inverse functions. If you have an inverse function, then the following statements are true. If f is continuous on its domain, then f inverse is continuous on its domain. I think that makes sense because we're just reflecting our figure. If it's increasing, then f inverse is increasing. Oh, okay. If you look at this one is increasing, this one's increasing. Oh, okay. That maybe didn't make sense to you at first, but hopefully, I mean, think about it. If your stock price over the course of time, time keeps on going on and the price keeps on going up, if you switch those two around, the price going up, the time keeps on going on too. I don't know if that helps you or not, but that's the idea. And then the same idea for decreasing for this one here. And then if f is differentiable at c and f prime of c does not equal 0, then f inverse is differentiable at f of c. Okay? This right here is our y coordinate. This gets a little confusing for students, but think about this. This is like your b coordinate. And so if we're differentiable, this is like your a. And then f of c would be like your b. Well, we already said that that's your b over here. So what has to happen is that I have to plug in the b into the inverse function to get out my a. We're going to be working around it a little bit there. I'll try to elaborate on that in a minute. And then one side note that I already mentioned, this inverse notation does not mean the reciprocal. That's a no-no. This is just convenience notation, and so f inverse, just that's all it means, is that we read it like that. Okay? Now, this is the theorem from this section. And this is where the a's and b's come about a little bit. Let f be a function that is differentiable on an interval I. If f has an inverse, g, then g is differentiable at any x for which f prime of g of x does not equal 0. This just means that we're not going to divide by 0. Moreover, g prime of x is equal to the reciprocal of what happens at f prime of g of x. Now, like I say, this is kind of confusing, But let me see if I can explain this a little bit better. So the crux of the problem is that this theorem right here refers to really this example that we did earlier. And I didn't finish the example. It says write the equation of the tangent lines. I didn't do that, but I should go do that. And that's what I did here in the red for F and the green for the G. Now what happens with this is that my line right here, look at the slope. The slope of the F line is 4. Well, what happens to the slope of the G line at those particular points? Well, it's going to be 1/4. They're reciprocals of each other. I hope you can kind of see that. And so that's what they're saying here. Now, why is this nested stuff in here? Well, if I take and I say that the point AB is on G. Okay, this might be reverse of what I said before, but I put AB on G. That means that G prime of A is going to be equal to, well, let me do this. I know that BA is on F then. And if I know what F prime of B is, F prime of B is going to be one value and G prime of A is going to be another value. What's true about these two? Well, they're going to be reciprocals. So if I'm finding what G prime of A actually is, well, that's going to be 1 over F prime of B. Well, the question becomes, what's another name for this B? Well, another name for this B would be, instead of B in this point, it'd be G of A. So this B right here could be G of A. So that's where this is coming right here, is that I'm plugging in the x coordinate into G prime, although I might not be able to find it or whatever. But then what do I plug into the F function? Well, I got to plug in the y coordinate of G, which is the x coordinate on F. Those two functions would give me a reciprocal slope. So really it's just saying these things right here, okay? And you can read this little note on the side, which can maybe help you as well, okay? Now I got to get to some examples. This video is getting long, I apologize. Find the tangent line approximation to the inverse of this function at x equal to 3. Approximate f inverse of 3.1 using your approximation. So in other words, maybe we can't find the inverse of this. Switch x and y and try to find the inverse. I think you got to get into a whole bunch of quadratic stuff. So what we want to do is, first of all, this says that x equal to 3. Well, this x equal to 3 is the x coordinate on my inverse. So if I think of G being my inverse, instead of writing F inverse, well, I can do that too. I have F inverse of 3 is equal to some value. What is that value? Well, that means then my point, I think a better way to do it is 3 blank is like that on F inverse. And then on F, what's going to happen? Well, I'm going to have the point blank, comma, 3. So if I take 3 and set it equal to this, I'm going to get x values, and you can try this. 3 is equal to x squared minus 2x plus 3. The 3's cancel out. X squared minus 2x is equal to 0. So I'm going to get 2 and 0. But I gave you x greater than 1, so this would be a 2. That means that my point on here is equal to 3, 2. I hope you sorted that out. So this is on F, and this is on F inverse. Now what happens is that I want to find the slope, but I don't want to find the inverse function to go ahead and find the slope. So I'm going to find F prime. So F prime would be equal to 2x minus 2. And then I can find the inverse at 2. I'm sorry, the derivative at 2. F prime of 2 is equal to, plug it in here, I get 2. So F prime of 2 is equal to 2. So what's the slope going to be on F inverse? Well, this is the slope on F, and so the slope on F inverse is going to be 1/2. So there's my point. So then I have a point and I have a slope. I can write this approximation line. So this would be y minus 2 is equal to 1/2 x minus 3. And then you could plug in 3.1 into this to get an approximation. I'll finalize that later, but you can do that. I know this is a little confusing to get your head around it. Main thing is that inverse functions, if you take corresponding points, their slopes are going to be reciprocals. Now this is what the book problem would look like. It's kind of the same thing. They want to find f inverse prime of a. And so what we have now is that, I got to get that keyboard out of there. I don't know why it's there, but so if I take the 3, remember a is equal to 3, that's on the inverse function. So I'm going to have 3 comma blank on f inverse. And then over here, I'm going to have on f, it's going to be blank comma 3. This turns out to be the same exact thing. So I get 2, and it's just worded differently. That's all I wanted to show you. And then this one is here is 2. So if I want to find f inverse of a, I have to find f prime of x, which would be 2x minus 2. The reciprocal of that is going to give me that. So I'm going to go f prime of 2 is equal to 2. So this slope over here is 1/2. And so y minus 2 is equal to 1/2 x minus 3. Okay, that would be finding the, and now I can just plug in a in here for this value right here, and that would give me f prime of, oh, I take this back, sorry. I went too far here, sorry. That's not there, but it's just my slope. And so this would be equal to 1/2. All right. I hope that you understand this. We'll work on the problems in class together, which helps us out a lot. And I'm sorry that this is so long. Take care. Have a good day.